Moving on to our AP style questions. Our first one here, we have a multiple choice. Three forces act on an object that is moving to the right at a constant speed. What that means in terms of forces is that means our acceleration is 0. So what does that mean about the forces themselves? Well, the first is the vector sum of the forces must equal 0. That just means that the sum of the forces overall adds up to 0, and that is our correct answer. For B, all forces must be parallel. That's not necessarily true. We could have a situation where one force is like that, one force is like that, one force is like that, and they all cancel out. The magnitudes of the three forces must be equal. That's also not true. You could have one big force going to the right, two smaller forces going to the left, and that would result in no net force and no acceleration. Last option, the situation is not possible. I've just shown two examples of how it's possible, so that one's not correct either. For this next one, we have a situation where we have a tractor trailer, and the trailer has 4 times as much mass as the tractor. What we're doing is we're comparing two forces. We're comparing the force that the tractor exerts forward on the trailer, and we're comparing that to the force that the trailer exerts backwards on the tractor. So we want to know how those two forces compare. Well, this one should pop out at you because this is a situation where the trailer exerts a force on the tractor and the tractor exerts a force back. And Newton's third law tells us that those forces are equal. Okay, equal and opposite. So it's got to be equal forces. We've seen from the lab and other situations the mass is irrelevant. The forces will be equal no matter what the difference in mass is. Next one, we have a cart with a mass of 10 kilograms is moving without friction along this surface shown, and there's two forces acting on the cart. We have one force going to the right with 10 newtons and another going up at an angle here with 30. And we want to know which of the following describes the possible motion of the cart. What I'm going to do, and we're thinking about the horizontal motion of the cart, I'm going to go ahead and break this 30 into x and y components. So we actually do need to do a little bit of math for this one. So this x component is going to be 30 cosine of 60, which is equal to 15 newtons. I could also find my y component. I do 30 sine of 60, and it ends up being about 26 newtons. But all of these scenarios are dealing with the horizontal motion of the object, so I really don't care about that y force. Breaking this up into, or thinking about the acceleration now, we have 15 newtons of force going to the left and 10 newtons of force going to the right, which means that this object must be accelerating to the left. So I need to look for scenarios that involve accelerating to the left. So this first one, moving to the left and speeding up, that's going to mean that both my velocity and my acceleration are going to the left, and that's what I have, so that's a possible scenario. Moving to the right and speeding up, they would both be going right, so B is not a scenario. Moving to the left and slowing down, well, if my velocity is to the left, my acceleration would need to be the right, so that's not possible. Moving to the right and slowing down, that scenario does work. I have a velocity to the right and acceleration to the left. That would result in moving to the right and slowing down, and my acceleration would be left, which is what I know it's going to be. Moving on to one of my AP free response questions. So we have a situation where we have a box suspended from two ropes. One rope is pulling horizontally on the box, the other is pulling up at some angle. There's also the force of Earth acting downward on the box. That has a magnitude of W. Okay, and we want to first start by drawing the free body diagram. So I'm actually going to draw my diagram down here. I'm going to think about the forces, and I am going to use the names that I was given here. So F1, F2, and weight. So F1, the force from rope 1, is going directly to the right, like that. F2, the force from rope 2, is going up at an angle like this. And I know that either this angle, or I could actually put it as this angle, is going to be that theta. Okay, these two angles would be the same. So I'm going to say that theta is that angle there. And I have the weight pulling down on it. So there's my free body diagram. There is a weird thing that the AP exam will do, and that's that they'll tell you not to break the force into components on the first diagram. They want you to do that separately for whatever reason. So I know I'm going to need to do that because I'm eventually going to do my F equals ma, and I always break my forces into components before I do that. But so I'm just going to go ahead and do that off to the side here. We have this F2 at an angle. There are the x and y components. And since this is the angle I know, the x component is going to be F2 cosine of theta. The y component is going to be F2 sine of theta. Moving on to part B, I'm now asked what would happen if this angle here, theta, was increased so that it became more vertical. So I'm going to redraw that situation and look at what the implications would be of that. So the thing that I'm going to notice, and this is really the key to answering this question, is that no matter what, if we're looking at our y forces, the weight of the object has to be balanced by that y component of F2. And so that weight is not changing, which means as this force becomes more vertical, we actually can pull less at an angle and still have the same y component, right? The more and more vertical we pull, the greater and greater that y component is going to be as a fraction of our overall force. So that means that we can actually balance the weight here using less force. So F2 is going to be less than it was before. So I'm going to start by saying that F2 will decrease, and then I'm going to make the point that the y component of F2 must be equal to the weight. And the key there is that means that y component doesn't change. So as F2 becomes more vertical, we can say that we can produce the same y component with less force because we're pulling up more rather than to the left. So there we have our rationale for part 1 of B. Now, what's going to happen to the magnitude of F1? For F1, what I'm going to see is I've just now said that F2 is going to decrease, which means, okay, as we decrease F2 and get more vertical, this x component is only going to get smaller. So our y component stays the same, our x component is going to get smaller, and that x component is balanced by F1. So that means that F1 will decrease as well. What I'm going to say is that F1 balances the x component of F2. That's the first important point. And then as that angle increases, that x component is going to decrease. And there's really two reasons why. It's a double whammy here. Because F2 decreases as a whole, and there's a more vertical pull. So both of those are going to contribute to a smaller x component. So since the x component is smaller and F1 is equal to that x component, F1 is also going to be less. So there we have our conceptual ones. In C and D, we're actually going to do derivations here of F1 and F2. And that's actually going to be something that should help to reinforce what you just saw here, should help to justify what you just saw here. So I'm actually going to erase these two explanations just to give myself a little bit more space, and then I'm going to go ahead and derive an expression for F1 and F2 in terms of weight and theta. So for C and D, deriving these expressions, I'm actually going to start with setting up my max and meg. That's something that we're always going to do whenever we're doing a force problem. I'm not even going to worry about what I'm actually looking for. I'm just going to set these up. So in the x direction, I have this F1 minus F2 cosine of theta, and that's going to be equal to my mass times my acceleration, but this object isn't moving, so that's simply equal to 0. So from my max, I can say that F1 equals F2 cosine theta. Moving on to my y, the forces that I have in my y direction are F2 sine of theta, and that weight, once again, that acceleration is 0, so that means that F2 sine of theta is equal to my weight. So what I ultimately want to do here for part C is I want to derive an expression for F2 in terms of W, that weight, and theta. So what I see right off the bat here is I have an equation here that only has F2, W, and theta. So I'm going to use that. I'm going to use that y equation, F2 sine of theta equals W, and so that means that F2 is simply W divided by sine of theta. When solving for F1, I'm going to use my x equation. I know that F1 is equal to F2 cosine of theta, and although that's a correct expression for it, I need to find F1 in terms of W and theta, and that is not in terms of W and theta, so what I'm going to do is I'm actually just going to substitute in that expression I just found for F2. So I'm going to say F1 is equal to W over sine of theta times cosine of theta. And that's an acceptable answer if you leave it like that. However, if you're feeling fancy and you would like to use some trig identities, cosine over sine is actually cotangent, so you could say W cotangent of theta. Or you would actually say W over tangent of theta. Any of these are possible. Moving on to my next AP style question, we have an experimental design one, your first one of the year, I believe. And so in this situation, we have a student in a lab has a cart with an unknown mass, and that cart is being pulled by a motorized cart here that will pull it with a constant but unknown acceleration. Okay, and what we want to do is we want to find the mass of the cart without using the scale. So what I'm actually going to do first to help myself visualize it is I'm going to draw a little diagram here. So here's my cart, and we'll say it's being pulled by my motorized car, some string there, and that's causing it to accelerate to the right. Okay. I'm also going to draw a free body diagram here for that cart. Think about what forces are acting on it. So we have the force of the table pulling up on the cart. We have the force of the earth pulling down on it. And we have the force that the car is pulling on the cart with, accelerating it to the right. So if I'm thinking about how I could find the mass, right, what things could I measure, what things would I measure? Well, one thing that would definitely be useful is that unknown but constant acceleration. The other thing is probably how much force we need to make it accelerate. And really the reason why I'm thinking about that is I'm thinking about good old F equals ma. So what quantities are we going to measure? We're going to measure the acceleration of the cart and the force and the pulling force from the car. Moving on to question or part 2, what equipment would be used for these measurements and how would this equipment be used? So, and I'm going to draw a little setup. There's a few ways of doing this, of measuring these two quantities, and that's really what we want to think about is what were the two things we wanted to find and what could we use to get those two things. We want to make sure we address both of them. So I'm going to say use a motion detector to find the acceleration, and what we're going to do from that is we're going to get the slope of the velocity versus time graph. And we can write this a little bit more informal than the procedures that we do in a formal lab report, and that's okay. The second thing we need to find is the pulling force. So to do that, I would use a force probe. We have the spring scales, which are the old school way, and there's also newer ones that we use in the collisions lab. They can measure a pulling force in addition to a pushing force. And what we'd be doing, okay, is connect the probe to the cart and have the car pull on the probe itself. Okay, and that would allow us to get that pulling force from the car. Thinking about a quick diagram here, I'm going to draw my motion detector sitting there. Okay, and it doesn't exactly have to look like the motion detector. Boxes are great little pictures. And then I'm going to have my cart with my force probe on top of it. And then I'm going to have my motorized car here. And like I said, that's going to be pulling directly on the force probe so I can get that force reading as we accelerate to the right. Next question, we want to describe the overall procedure. Okay, we want to give enough detail so that another student could replicate this experiment. So what we're going to do, and this is basically the how would you run a trial part of this, we are going to start the motion detector, I'm just going to call it MD, and the force probe, FP, all right, and turn the car on. And we're going to record the force and the velocity versus time graph as the car pulls the cart across a horizontal surface. One last thing I'm going to add, and the AP actually doesn't always make you do this, but I'm going to say repeat for multiple trials, because we always want to take more than one trial in case there's errors or something like that. The last part we want to do is we want to talk about how these measurements we just took are going to allow us to calculate our mass, which is ultimately our goal. This section can kind of be a blend of equations and words. So the first thing I would do is I would find the acceleration by getting slope on the velocity versus time graph. Next, I have my F equals ma. Sum of the forces equals ma. So thinking about the forces acting on it, it's just going to be the force of the car is equal to the mass times the acceleration. So I'm going to use this equation with that force that I found from my force probe and the calculated acceleration that I got from the slope of my velocity versus time graph to get the mass. And what's nice is to rearrange the equation so it's pretty clear how that's going to happen. That mass is simply going to be the force of the car divided by the acceleration, and that's going to allow me to get the mass of the car. So that was the first part there. I'm going to move on to part B here, and I'm going to give myself a little bit of room, so I'm going to delete all this writing here, and we'll look at what part B is asking. So for part B, it tells us that we now have a way of varying the force exerted on the cart. It really doesn't matter how we do that, but we can vary that force. And we're going to go ahead and do that and look at how that affects the acceleration of the cart. Okay, so we have a series of trials, and we end up producing this graph here showing the acceleration as a function of the force applied to the cart, that F car. So we want to know how we could get this mass from the graph. So the first thing I'm going to think about is what is the relationship between those variables? And I had this before, that the force of the car is equal to ma, the mass times the acceleration. So I'm going to go back to something that we talked about during the linearization unit, and that is, in this case, we know the relationship between the force and the acceleration. So we should be able to predict what the graph of acceleration versus force applied will look like, and we should be able to say what the meaning of the slope is. So if you remember, the first thing we want to do is we want to isolate whatever we put on our y-axis, that dependent variable. So I'm going to say that A is equal to the force of the car divided by the mass, and I'm going to rewrite that because I'm going to pull out any constants, which mass is a constant. So I'm going to rewrite it as acceleration is equal to 1 over the mass times the force of the car. And now I'm going to compare that to y equals mx plus b. Acceleration is what I have on my y-axis. The force of the car, the applied force, is what I have on my x. And so what this tells us is, number one, it tells us that our y-intercept should be 0, and it tells us that our slope, and we got to be careful, we have m for mass and m for slope, is going to be equal to 1 over the mass. Okay, so how could we get the mass of the cart from this graph? Okay, the slope of this graph is going to be equal to 1 over the mass. So what we could do is we could find the slope, right, and solve for mass that way. Now I'm going to write out a little equation down here. Our slope is equal to 1 over our mass, so our mass is going to be equal to 1 over our slope, and that's ultimately how we could determine what the mass is using that graph. For the second question, and I'm just going to kind of come up here to write the answer to that, explain why the graph does not intersect at the point 0, 0. It should intersect at the point 0, 0. We see that from our equation. Our y-intercept should be 0, but clearly it is not. Okay, this graph will continue on down and have a negative y-intercept. So this is likely a result of sources of error. Okay, and there's two real big ones that could result in this. Number one, it could be uncertainty in measurement. We always have that. All right, it's possible that our equipment was calibrated a little bit off, and that could lead to the data being skewed one way or the other. So that would be one thing that result in the graph not intersecting at that point 0, 0. The other thing that we could say is it could be that there was some friction. Right? It said from the start that it was not truly friction, or that it was frictionless, but in reality it's probably not truly frictionless, and that a little bit amount of friction, okay, could account for this. And that actually probably makes the most sense, because if we think about this point here, right, where it intersects the x-axis, this is saying that even if we apply a certain amount of force, there's zero acceleration. Why would there be zero acceleration even though we're applying a force? Well, that would be because we have a small frictional force acting backwards on the object. Okay, so at this point the applied force and the friction are equal, and it results in no acceleration. And then as we increase the applied force, we start to see that acceleration. So either one of those is a possible answer. The second one's probably the more likely one, but it could be uncertainty in measurement as well.